Today we're going to continue with different electrophilic addition reactions. The first reaction we want to look at is the reaction between an alkene and an halogen. In this case, we're looking at Cl2. And the first thing I'm going to do is show you the wrong mechanism. Now, the wrong mechanism is going to look a lot like other mechanisms that we've seen before. The alkene reaches out, hinges away from one of the two carbons in the alkene, pushes into some electrophile and bounces off some leaving group, and we end up forming a carbocation. This is what we would expect to occur in this reaction based on every other reaction that we've seen. But in this particular reaction, something else happens. Instead of forming a carbocation, one of the halogen's lone pairs circles back around and makes this triangular intermediate right here. This particular intermediate is unique, and what it allows the molecule to do is skip the formation of a distinct carbocation. And instead we end up with what's called a chloronium ion intermediate, or if we use molecular bromine, it becomes bromonium, and I'll spell this for you in a second. And more generically speaking, it's called an halonium ion intermediate, where you have a halogen bridged across two carbons. Now, these are not the boron type of bridges where we're sharing electrons between three atoms. These are distinct bonds that exist. There's a bond that connects the carbon to the chlorine, another bond that connects this chlorine back to that carbon, and a single bond right there. Full-on regular bonds. The reason that this is better than a carbocation is while there is a positive formal charge on the chlorine, and you do have a tremendous amount of strain associated with this triangle, you ultimately give everybody an octet. So this ends up being a better situation from the perspective of overall molecular stability. And this idea of skipping the carbocation and doing something else interesting instead is the unifying theme of the different reactions we're going to look at today. So they have the same basic features of electrophilic addition. The pi bond pushes out into an electrophile and something falls off of that electrophile. But today we're going to see this kind of this back attack, where the electrons come back in and prevent the formation of the carbocation in the three mechanisms that we're going to see today. In the next step of the reaction, there's a backside attack. The chloride ion that just fell off is going to come around and hit this partially positively charged carbon in the back, inverts the stereocenter, so this methyl group used to be coming towards you, and now it's going away from you, and you end up finishing up your reaction. So 2 steps, this reaction is done. I named the product here mostly so that you can appreciate the chiral centers that we added in this reaction. We started off with a compound that has no chiral centers. There's no chirality anywhere in this starting material, and our product introduces 2 new chiral centers. Whenever you start off with a starting material that does not have a chiral center, and you end up with a product that does have a chiral center, we expect for the reaction to produce a 50-50 mixture of enantiomers, meaning that in addition to producing this compound at that first step, where the pi bond reaches into the screen to plug into that chlorine, the pi bond is also, with equal probability, going to reach out of the screen to produce a chloronium ion intermediate that is the enantiomer of this other chloronium ion intermediate. And when the chloride ion comes and pops open your chloronium, you're going to end up forming the other enantiomer. So we end up with a racemic mixture of these 2 enantiomers of each other. And the name helps us see that they're enantiomers because we've switched both of the chiral centers from R to S. What does the energy diagram for this reaction look like? Well, there are 2 steps. And the first step is the rate determining step. So we come up in the first step to this chloronium ion, which has a net positive charge, has a bunch of angle strain, and so this is an uphill climb. And then when the chloride ion attacks this thing from behind, then we drop down to a lower energy state overall. The halonium ion, and this is the spelling of that, and if you are talking specifically about chlorine, then the HAL is replaced with chlor, so it's chloronium or bromonium. But generically speaking, this is an halonium ion, and this is the high energy intermediate. And remember, we formed the halonium ion intermediate because while it is high energy, if we didn't cycle back with that blue arrow and just formed a distinct carbocation, that would involve an even higher energy state. So this is an energetic choice that the intermediate makes, and it cycles one of these lone pairs back in that same initial step to prevent the formation of a distinct carbocation intermediate. The stereochemistry that exists between the two chlorines or the two halogens, if we were using Br2, we just end up with bromines on this position. Notice how in both of the products that I get, both of these enantiomers, the halogens are anti relative to each other, or trans, because this is a ring system. They end up on opposite sides of the ring, and that's because of this backside attack that occurs here in the second step, where this chloride ion has to approach from the backside of that carbon-chlorine bond, which is going to force it to, if the chlorine is going away from you into the screen, then the chloride ion that attacks has to hit it from behind, which means it would end up coming out at you. The other key feature that we end up with here is thinking about what's the difference between molecular chlorine and molecular bromine in this reaction. Well, notice that the rate determining step is the first step when we make this halonium ion. And while the halonium ion is better than a carbocation, it's still not excellent, and we still have a problem with net positive charge and all kinds of angle strain and torsional strain associated with a three-membered ring. Notice how there is a distinct chlorine involved. The molecular chlorine is definitely involved in the rate determining step. So whichever of the halogens is the most reactive will ultimately cause this rate determining step to go faster. So if I take the chlorine out and replace it with Br2, then you should be able to ask the question, well, would it go faster or slower, and answer that question. One of the common mistakes students make is they confuse the relative reactivity trend of halogens with the reactivity trend of halogenic acids. The most reactive halogenic acid is hydroiodic acid because it's the strongest acid. For the molecular halogens, these are not acids, and their reactivity is actually flipped. And this is based on electronegativity. Two fluorines are going to fight. They're not going to be stable trying to share a bond because they're so electronegative. Iodine is the least reactive of the molecular halogens. And so again, when you're asking questions about reactivity of halogens, you have to keep straight whether you're dealing with the halogenic acids or the molecular halogens. This reaction deals with the molecular halogens, and chlorine is more reactive than bromine. Therefore, the reaction as I've drawn it up here would be faster than the reaction if I had showed it instead with Br2, because Br2 is less reactive. Now let's consider a slight variation of the reaction we just looked at. So the name of the reaction that we just looked at is the halogenation of an alkene. In a related reaction, we can add, this is hypochlorous acid or hypobromous acid if we wanted to end up with the bromine equivalent of this. And instead of taking our alkene and turning it into two halogens, it takes the alkene and turns it into a halogen and an alcohol. And similar to the reaction we just looked at, the final position of the halogen and the alcohol, they will end up being anti relative to each other. And the reason that they're anti has to do with the mechanism, so we'll dig into that in just a second. Notice also that I started off with a compound that has no chiral centers. And so if I end up producing a product with two distinct chiral centers, then I should also produce a 50-50 mixture of the enantiomer of that product. So just like the previous reaction, we're going to go from an alkene, and we're going to put two things on that alkene, and those two things in this particular example produce two chiral centers, so I would expect a racemic mixture. Both of these reactions, the one that I just looked at and the one that I'm looking at now, are useful because we took a single functional group, this alkene, and we're turning it into two separate functional groups. In the previous reaction, you're turning it into two separate alkyl halides, and in this reaction, we call this a halohydrin, H-Y-D-R-I-N. And because the halogen and the alcohol, this hydrin, are coming off of adjacent positions are called by organic chemists vicinal positions. So this reaction is called the formation of a vicinal halohydrin. That's this type of reaction. The mechanism is still electrophilic addition. So mechanistically, Well, fortunately, we don't have much to learn here if you remembered the previous mechanism that we just looked at. And the reason for this is these hypochlorous acids and hypobromous acids will undergo decomposition at all temperatures to produce a mixture of molecular halogen and water. Bleach often contains sodium hypochlorite, which is the base form of this, and they put that in water. So they take sodium hypochlorite and they put it in water. Occasionally the hypochlorite protonates to produce hypochlorous acid. So in a bottle of bleach, you're going to have some small quantity of this. As soon as this forms, it decomposes. Now, equilibrium does not favor the formation of the decomposition product. So when bleach decomposes, it does produce a small amount of gas phase molecular chlorine. And you can smell this. This chlorine will come out of solution and forms a gas that actually drives the equilibrium forward. And often there are microscopic pores in your bleach bottle that are small enough to allow the chlorine to escape. And so if you have a bleach bottle that contains sodium hypochlorite, you can probably smell it, especially if the bottle is older, and you can actually smell the distinct odor of chlorine coming out of that bottle. And this means that over time, actually, bleach loses its potency. Not all of it, but quite a bit of it. And so if your grandma has a bunch of bleach stored for the zombie apocalypse to purify her water, and she's had it in her basement for 20 years, it's about 19 years expired. So bleach doesn't have an infinite shelf life because of this chemical reaction right here. I'm not going to show the mechanism of this reaction because there are no carbons involved, and so I do not care. But you have to remember that anytime you add hypochlorous or hypobromous acid to a solution, the actual players in the chemistry are molecular chlorine and water. So the first step of the mechanism for this reaction to form a vicinal halohydrin is the exact same first step of the mechanism that we saw in the previous slide. So this three-arrowed mechanism, electrophilic addition, pushes out the pi bond into the chlorine, bumps off the second chloride ion, and then a lone pair cycles back to form the chloronium ion intermediate. In the previous reaction, we saw the chloride ion come and pop open this three-membered ring, but I have directly added water to my container, and when water is present, we expect water to do the bulk of the chemistry. I'm just going to show both mechanisms for both enantiomers simultaneously. If I were asking you to do this on an exam, I would not want to have to look at this twice, so I would just ask you to show one product. So the water comes over and pops open the ring, and we're not quite done here because we still have to remove the hydrogen from that water that I just brought in. As we've seen before, when water is present, water does the bulk of the chemistry, so we expect the water to do the deprotonation step, and this is how I end up forming both enantiomers of my product. A couple of notes. Because of the backside attack that occurs in the second step, we still expect an anti-addition of the water and the chlorine in our final product. So just like the previous reaction, it's still anti. And the second comment on this one is, in this three-membered ring, there is still some kind of residual carbocation character. This positive charge gets shared across the ring system, and what happens is the carbon that is more substituted will actually carry the bulk of the positive charge. This means that when the water comes in and attacks this three-membered chloronium ion, the water will come into the more substituted position with higher probability. And so across the double bond, we expect the water to end up, the alcohol, this is the end product of that water, this alcohol will end up at the Markovnikov position. The energy diagram for this reaction will look very similar to the previous energy diagram, but there is one more step. We have 1, 2, 3. The first step is still the rate determining step. That's when we form the chloronium ion intermediate, which is better than a carbocation, which would have a higher energy. When water pops open that chloronium ion intermediate, we drop way down in energy, and then a final deprotonation step to get to our final product. For the next reaction we're going to look at, which is the epoxidation of an alkene, the key reagent that we use is a peroxycarboxylic acid. Notice that it has kind of the same structural features of a carboxylic acid, but an extra oxygen. So it's a peroxycarboxylic acid. The shape of this molecule is actually locked into this pseudo five-membered ring. And that's because this oxygen up here can actually form an internal hydrogen bond across this gap right here. Kind of locks it into a 5-membered ring. It's not a full 5-membered ring, but it has that characteristic. Now what we're going to do is go ahead and add an alkene to this. Now the mechanism that I've shown here is not the full mechanism, because remember the theme of today is don't make carbocations. But it shows you part of the mechanism and helps you appreciate how this is kind of a typical electrophilic addition reaction. The pi system hinges out into this external oxygen that allows the peroxide bond to break when the bond swings down to make a double bond. So this is like a bond hop. It goes from being a sigma bond right here, and it's going to fold over to make a pi bond right there. This is a very unique mechanism because it has 4 total arrows. Very rare that we see 4 total mechanistic arrows in a single elementary step, but that's what we have here. And the last 2 arrows just kind of finish things up. And notice, just like we saw before in the formation of the halonium ion intermediates, we're also going to make a 3-membered ring. Now I drew these bonds at just ridiculous angles just so you can kind of see where all the atoms go. This oxygen that is closest to the carbonyl carbon ends up being the new carbonyl oxygen, and the oxygen that is further away ends up tacking on to what used to be my alkene and becomes the epoxide. I can redraw this and with better bond angles right here. This is a very rare mechanism, one that you kind of have to memorize. And so the epoxidation of an alkene is merciful that it's concerted. Everything happens in a single step, but the 4 arrows on this one, they're hard to keep straight. You get all tangled up in those arrows if you don't practice this one. So practice it. The product of this reaction has a chiral center right there. And so I'm going to make, let's say that I made S, and the name of this is not a nomenclature system that you're responsible for yet. So let's say that this is S2-methyl-oxyrane. If we go back to our starting material, this original alkene does not have a chiral center. And therefore, if I introduce a chiral center into my compound, I am also going to make an equal amount of the enantiomer, and we end up with a racemic mixture of products right here. Let's look at the energy diagram for this reaction. Well, it's concerted, so that means it's one step. And we can actually, if it doesn't actually drop lower in energy, Le Chatelier's principle allows you to kind of manipulate the energy starting and stopping points. So if you want to flood the system with your peroxycarboxylic acid, that actually raises its energy and leads to a downhill reaction. And that's how we cheat our thermodynamics using Le Chatelier's principle. This reaction I've shown the energy diagram for propene, or propylene is its common name. And there is a step where in this reaction the pi bond is folding out into that oxygen. That means for kind of a flickering moment of time, there is a buildup of carbocation on this secondary position right here. If we compare how this reaction right here looks energetically with, let's say, ethylene, or ethene is the systematic name, when you try to draw the same arrows but you use ethene instead, when the pi system hinges out into the oxygen, it's going to leave behind a primary carbocation on ethene, the red. The black would leave behind a secondary carbocation. The red would leave behind a primary carbocation, and therefore we would expect a higher activation energy barrier if we had used ethene as our starting material instead of propene. A higher activation barrier would mean that this reacts slower, and it reacts slower because it is less able to stabilize a carbocation intermediate. If we consider an example that takes us in the opposite direction, this is 2-methylpropene. When this pi bond folds out to attack that oxygen in the first step of my mechanism, it's going to leave behind a tertiary carbocation for that flickering moment while we crawl uphill in energy. And since a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, we see the activation energies trend smaller with more substituted alkenes, and that means it's going to go faster. The last reaction that we want to talk about is a reaction that does not have a mechanism that we're going to worry about. Ozonolysis splits a pi bond and puts 2 oxygen atoms on it. That's as much of the mechanism as we need to worry about. There are two different sets of reagents that we use in ozonolysis, and notice the numbering system. This is something that we've now seen before, and you have to first add in the ozone, and then it waits until you follow it up by adding in water and zinc. Ozone is a strong oxidizing agent. In fact, there are ozone air purifiers, and what they do is they electrocute air, they make a small quantity of ozone, and the ozone will start to tear through bacteria, pollen, dust, etc., and it probably does it in much the same way by clipping apart double bonds. It can do other things as well. So in the first step, we add in this strong oxidizing agent, and in the second step, we follow it up with a reducing agent, and that's what the zinc does right here. This is useful when your starting material is fairly polar. If your starting material is less polar, then you have to use this set of reagents right here. Ultimately, both sets of reagents will give you the exact same type of products, where we take this double bond and we clip it, and then we stick oxygens onto the broken fragments of the pi bond. So mechanistically, I like to think about this reaction as if I took this pi bond right here and just cut it right in half to produce two broken fragments, and then I stabbed those into molecular oxygen, and we ended up with our final product. I don't care which set of reagents you guys choose to use. You probably are going to memorize the first one because that's what students typically do. It's a little easier to remember. I will show you either set of reagents on an exam, but you should recognize O3 because the only time we see O3 in organic chemistry in our textbook is when we're going to undergo an ozonolysis reaction. And so we'll see ozonolysis for alkenes, and then in a later chapter we'll also look at ozonolysis for alkynes. But in both cases it just clips that double bond and ends up putting oxygens on those broken fragments. I had a semester where students were asking me about more details about the mechanism, and the short answer is I don't know. There is an intermediate I'll show you in a second. So as a joke, I said you can make up any mechanism you want, and so a student did just that. This is a diagram that a student drew out, and I'll try to narrate what's going on here. So this is cyclopentene as the starting material, and in this proposed mechanism, a ninja approaches the cyclopentene, draws his sword, and cuts the cyclopentene double bond. Okay? Once the double bond is cut, then the ninja throws two oxygens right here, like ninja stars. They fly through the air, and they land on the cyclopentene until we get the final product now, where the alkene that used to be there is now cut and then capped off with two oxygens. This was drawn by Nathan Anderson and was fantastic. Here is one of the problems that I gave you in the lesson, and this shows the ozonolysis reaction as well as one of the known intermediates of that reaction. And you can kind of see this 5-membered ring here that still has that peroxy bond. We don't have to worry about exactly how that's formed. You're welcome to draw ninjas as your proposed mechanism. And then that crumples kind of in the presence of water and zinc, and we end up with this ketone and aldehyde. The question asks you to kind of keep track of the carbons. So I've numbered the carbons here. This particular molecule is a pentene. This would be a Z3-methylpentene. Will be the name of this starting material, and I've numbered the parent chain 1, 2, 3, 4, 5, and then off of the 3 position is my methyl group, so I'm just going to refer to that as 3'. The numbering here is not that important. I just want to keep track of where all these carbons go. And so when it forms the 5-membered ring, it splits across this double bond, so carbons 1 and 2 are down here, and then 3', 4, and 5 are up top. And then when the water and the zinc kind of clip this 5-membered ring apart, carbons 1 and 2 end up on the bottom, and 3', 3, 4, and 5 end up on top. So this is just an exercise in keeping track of where the carbons are going during ozonolysis, and it kind of helps you see what's going on in this reaction. Ozonolysis is used largely as an analytical tool, and so converting an alkene into ketones and aldehydes is actually a functional group transformation that we will show you how to do in the second half of organic chemistry. In this particular case, you can do it in one steps, but you do end up clipping your compound into smaller fragments. And so one of the things that they'll do in the laboratory is often they'll start off with a compound that is not very polar. And for reasons that you would appreciate in the laboratory, it is difficult to analyze and purify nonpolar compounds using a lot of the techniques that we have in organic chemistry. So sometimes what they'll do is they'll take an unknown compound, they'll subject it to ozonolysis. These oxygens that get added on here make it much easier to purify and separate and clean up your products, and then you have to stitch them back together again to figure out what the original starting material looked like. So I'm going to un-ozonolyze this. So remember, in ozonolysis, what we did is we stuck two oxygens on the broken fragments of alkenes. And so I'm just going to take the oxygens off. I'll just do the ninja reaction in reverse. So I'll take the oxygens off, and then I'll kind of line up the pieces, and then I'll just stitch them back together again. So compound X would need to be 2,4-dimethyl-2-pentene in order for ozonolysis to produce these fragments right here.